Hey everybody, Mr. Piercy here, and we're going to be starting a new unit today where primarily this unit is actually going to be talking about quadrilaterals and the different types of quadrilaterals that we have and their properties associated with them. But before we start talking about quadrilaterals specifically, we're going to talk about polygons in a little bit more general terms. Um, Now this set of notes, this lesson that you're going to be seeing here should follow an investigation that you're doing that generates where these rules come from in the first place. So ideally, it's not going to be something that should be brand new to you. You should have seen some of these concepts when you wrote your conjectures for an investigation that precedes this. But let's go ahead and start taking a look here. Again, the investigation that you're talking about is starts off essentially with this. How do you determine? So it's well established in geometry that the sum of the interior angles of any triangle in Euclidean geometry has a sum of 180 degrees. Well, what if the polygon has more than 3 sides? What if it has 4 sides, 5 sides, 6 sides, and so on? Well, again, pretty much anybody you ask, if you said, well, the 4 angles of a quadrilateral, if you add them up, how much do they equal? Almost everybody's going to say 360 degrees because it's just something that they memorized. But why does it have 360 degrees in it? And if you if you went beyond that, if you went to a pentagon, hexagon, and so on, how would you be able to figure that out if you don't have that stuff memorized? Well, what we see in the box here where it says Theorem 8.1, Polygon Interior Angles Theorem, well, what we're doing, and this is what you should have seen in your investigation, is from a vertex, from any vertex in the figure, we're going to draw in however many diagonals that there are. And so, for instance, you can see that I have in the box, there's a hexagon, a six-sided figure. And so from one vertex, we're able to separate the hexagon into 4 separate triangular regions. And if each triangle has a sum of 180 degrees, we can say, well, if there's 4 triangles or 4 triangular regions that we can separate a hexagon into, and each triangle has 180 degrees, then we can take the number 4 and multiply it by 180, and that will tell me how many, what the sum of the interior angles are going to be for a hexagon in this case. So this is what we're looking at here. Again, this is kind of following along what you saw in your investigation piece. This should just be kind of follow-up review for that. Okay. And now let's take a look at how we're going to use it. All right. So here we have, again, another hexagon. Oop, I don't know why I'm getting... There we go. Let's try that now. There we go. Hexagon has 6 sides, obviously. So if we were going to use that formula to find the sum of the interior angles of a polygon, n in this case would be 6. So looking at the formula here, we're going to say n minus 2 times 180, where in this case n is 6. So I'm going to substitute 6 for n and say 6 minus 2 inside the parentheses multiplied by 180. Well, following our order of operations, we're going to do the combiner like terms inside of the parentheses first. 6 minus 2 gives me a 4, and 4 times 180 in this case gives me a sum of 720 degrees. Now this isn't something I expect you to memorize, as far as I don't think you need to necessarily memorize, oh, hexagons have 720 degrees in them the same way that you know triangles are 180 and quadrilaterals are 360. It's the rule that you need to remember because I'm not going to necessarily ask you just a hexagon or a nonagon or something. I might ask you for a polygon that has 36 sides or 21 sides, and you have to be able to figure that out. So the rule right here, that's the important bit that we need to make sure that we remember. Okay, so let's go ahead and move on here. Now, the last example that we saw talked about, well, if I know the number of sides, could I figure out what the sum of the interior angles are? The example that we're seeing here, they're giving you the sum of the interior angles, and they're going to expect you to work the equation in reverse, so that way you can figure out how many sides there are. And we don't need to necessarily rewrite the equation as a literal equation, although we certainly could. We can just plug in the numbers that we know and go from there. Well, we know the formula is n minus 2 times 180 equals whatever the sum is. In this case, the problem gives us the sum to be 1,260 degrees. So that's how we substitute the numbers into the formula there. And now we're going to work backwards to solve for n. So again, we can't do anything inside the parentheses because I don't know what n is. And we could distribute the 180 into the parentheses and say 360n minus, or 180n minus 360 is equal to 1260. But that would just give us more operations, more steps that we need to. Since the 180 is already isolated outside of the parentheses, we're going to just go ahead and divide both sides by 180, which gives us n minus 2 is equal to 7. And move the 2 over through addition now, and we can say that there are 9 sides in this case, so we have a nonagon. So a nonagon would be 1,260 degrees, all of the interior angles added together. Now, this is a very common application because if you can figure out the sum of the interior angles of a polygon, then we can use that value to figure out measurements of the interior angles. They don't necessarily have to be the same. So here we happen to have a quadrilateral. Now in this case, you don't necessarily have to figure it out because you don't have to use the rule n minus 2 times 180. You don't have to really use that rule right now because most people accept, that we understand that there's 360 degrees here. That's something that people have kind of committed to memory, and we can accept that for this problem. So taking the 4 angles that we have here, we're going to say, well, the 4 angles have to have a sum of 360. So we set up the problem this way, where we just say angle 1 plus angle 2 plus angle 3 plus angle 4 equals 360. We'll combine your like terms, and we're going to get x plus 318 equals 360, and then just move the 318 over through subtraction, and we would say that x in this case is 42. Now, since x happens to be the measurement of the angle, we can say we're done at this point. If there had been another angle in there that said like 2x or 3x or half x or something like that, we would have to go back and substitute it to find the measurement of each particular angle, but in this case we can stop here. So go ahead and take a moment, if you haven't already worked ahead of me, and find the sum of the interior angles of the decagon. Now, real quick before you pause the video and try and work this out, make sure you understand the common names for, say, the first 10 or really the first 12 polygons, because not always will you be provided a picture like you are here. Sometimes you'll just be asked, well, find the sum of the interior angles of this, and you have to be able to know, well, this type of polygon has this many sides. Okay? So go ahead and pause the video and figure out what is the sum of the interior angles of a decagon. All right. So looking at the figure here, well, decagon, the prefix deca means 10. Just like a decade has 10 years, a decagon has 10 sides. And you can see that easily when you just kind of count the number of vertices or count the number of sides in the figure. So we say n minus 2 times 180 to start the rule off, and then we substitute 10 for n. Working out the problem gives us a sum of 1,440 degrees. Now, one thing that I want to kind of mention here, this is something that, well, no, I'll save it for the next one. I'll save it for this one here. So here, example 2 and 3, kind of what we saw a second ago. We're given the sum of the interior angles now and say how many sides does it have. And using the fact that there's so many measurements inside, or so many degrees inside of a particular polygon, can you find the missing angles K and L in problem 3? So go ahead and work these two problems out rather, and when you're done, hit play again. Okay. So let's see here. The sum of the interior angles is 1,620. So again, I'm going to start off with my rule somewhere, wherever I typed it there. We're going to start off with our rule. It says n minus 2 times 180, and then substitute the 1620 for the sum, because that's what they were giving me. Divide both sides by 180, and then move the 2 over through addition, and I get 11 sides, which is called an undecagon, or you can simply refer to it as an 11agon. Out of the first 12, well, first 12, because there isn't one for, there's not a one-sided or a two-sided polygon, but from a triangle up through a dodecagon, a 12-sided figure, I would expect you to have those terms memorized, except for maybe this one. This one's kind of a weird one. Now, one quick thing, real quick, before I move on to problem 3. Oftentimes, you'll see a problem like this, but you'll see a problem like number 2, and instead of it asking how many sides are there, it might ask you, could you have a polygon that has this sum in it? Okay, so let's just say, for example, let's say we change the problem that says, can a polygon have a sum of 1,530 degrees? So working out the problem here, I'm going to say the sum is equal to n minus 2 times 180. So plugging in my numbers here, I would say 1530 is equal to n minus 2 times 180. And when I divide both sides by the 180, I'm going to get 8.5 to be equal to n minus 2. And at that point, we can stop. We don't need to say that n is equal to 10.5. It's not possible for a polygon to have a sum of 1,530 degrees, because what you're saying here is that I have half of a side. It's not possible. A polygon either has a side or it doesn't. If it's not closed, then it's not a polygon. Okay, so pay attention when you see questions like that. If you get a decimal answer working these types of problems out, we made a mistake. Or again, if the question is asking, can you do this? We'd have to say no in this case, because I can't have a polygon that has a part of a side. All right, so looking at number 3 here, what I'm going to do is, first of all, this one differs from the last one. In the last one, it was a quadrilateral, and we could just, oh, it was 360, no big deal. Well, if you don't know that a polygon, or if you don't memorize that a pentagon has 540 degrees in it, you do have to use the rule to figure out, well, how many, what is the sum of the angles in there? Now that I know that it has 540 degrees, now I can say, well, the 5 angles added up have to have a sum of 540 degrees, and just substitute the stuff in there. Now, since in the diagram they're showing that angle L and angle K are congruent to each other, I just called them X when I worked them out, and so that the 2 angles that we're looking for both have a measurement of 129 degrees. Now, this is the second part of the investigation that you would have seen, where we're talking about the, well, here we're looking at the sum of the exterior angles of a polygon. And what you would have seen in the investigation that preceded these notes is that, well, the sum of the exterior angles of any polygon has to be 360 degrees. It doesn't matter how many sides it has. The sum of the exterior angles are all going to be 360 degrees. Now pay attention to how they're drawn. It's almost like a pinwheel shape. It doesn't matter whether the arrows are pointing, you know, kind of clockwise or counterclockwise. However you draw the exterior angles, you're going to draw them in the same fashion all the way around the polygon. So keep that in mind as we're kind of looking at these. So in the first example, can we find the measure of the exterior angles? Well, out of the 4 angles that we have, they all have to have a sum of 360 degrees. Not because it's quadrilateral, but because the sum of the exterior angles of any polygon is 360. So combine your like terms, and we get 3x plus 174 is equal to 360. Then I can move the 174 over through subtraction, which gives me 3x is equal to 186. Divide by 3, and x is 62 degrees. Now, the other thing that I might do for a question like this would be to say, find the measure of the missing angles. So simply saying that x is equal to 62 may not be enough maybe actually want to tell me what are the measurements of the two missing angles. So I would just take the 62 and substitute it into the expressions to find the missing angles. Now, the last thing that you would have seen as part of your investigation uh, is we have some regular polygons. Now, regular polygons differ from polygons in general is that a regular polygon has to have all sides and all interior angles to be the same to each other. So keep in mind that's important as we move on. If I say I have a polygon or if I have a regular polygon. If you see the term or hear the term regular polygon, that implies that it has certain characteristics about it that other polygons may not have. So here we have, in this example, we're looking at like lampshades. It's in the shape of a regular 15-sided polygon. Find the measure of the interior angles and find the measure of each exterior angle. Well, finding the measure of the interior angles is going to be relatively easy because we know, using my rule here, I can find that the sum of the interior angles of a pentagon, I'm sorry, not a pentagon, but of a 15-sided polygon is going to be 2,340 degrees. Well, if each angle inside has to be the same, I can take the sum of that and divide it by however many angles there are. So in this case, I'm going to say 2340 divided by 15, so I can figure out the measure of each interior angle is 156 degrees. Now, conversely, I can say, well, since the exterior angles have to have a sum of 360 for any polygon, it doesn't really matter, I can take the 360 and divide that by 15 and find the measure of the exterior angles to be 24 degrees. Now, one of the things I want you to make sure you pay attention to, the diagram that I've added onto the left side here, where we're talking about particularly what I'm looking at is here where I'm looking at the exterior angle and the central angle. For a regular polygon, the measure of the exterior angles and the measure of the central angle, meaning the angle that goes from the center of the polygon to two consecutive vertices, those are going to be the same. So I can find the measure of the exterior angle or I can find the measure of the central angle using the same method. Now, real quick before you start looking here, if you want to see what this is, I realize that it's a little hard to see. This is just explaining the difference between convex and concave. Concave, there's a lot of, I don't want to say a lot, but there's more than one way that you could define or describe what a concave polygon happens to be. Here what it's showing you is that at least one of the interior angles is greater than 180 degrees. That would be a reflex angle, going way back to how we classified angles at the beginning of the year. Some people draw arrows inside, and so from head to tail, the arrows all have to kind of match head to tail going around the interior of the polygon. But as long as you kind of recognize that one of the vertices in some way kind of points into the interior of the polygon, then you should be okay. That's just the difference between convex and concave. So go ahead and answer these two questions here about the exterior angles and so on for a regular polygon. And when you have your answers, go ahead and hit play and see how you did with my answers. Okay, so hopefully we have good answers here. So looking at problem 4, we have a convex pentagon where the exterior angles are 66, 77, 82, 62. What's the measure of the fifth angle? Well, it's not saying it's a regular polygon, but that's okay. It doesn't matter. The measure of the angles always, for exterior angles, always have a sum of 360. So the 5 exterior angles add up to equal 360. Plugging in the 4 values that we know, we get 287, subtract that from 360, and that gives us the remaining angle to be 73 degrees. Now, in example 5, or problem 5 here, they are being specific. They're implying that it's regular, so we have a regular 9-sided figure in this case, and we want to know, well, what are the measures of the interior and the exterior angles? Now, it really doesn't matter which one you do first, because the measurement of an interior angle and the measurement of its exterior angle, they have to be supplementary. So in this case, you could have found one or the other first and then simply subtracted that number from 180. You just need to remember that they are supplementary to each other. So here we go. Depending on how you wanted to do it, I would say n minus 2 times 180 over n. So the sum divided by however many of the angles there are. In this case would give me 140 degrees. So the exterior angles, we just say 360 divided by the number of sides. So I get the measure of the exterior angles to be 40 degrees. Now remember, because the interior and exterior angles are supplementary, once I know one of them, I really know the other one. So if you remember that, you can use the 360 divided by n. I think it's just going to be a little bit more, a little bit less work than using n minus 2 times 180 divided by n. But it's a personal choice, whichever. As long as you get the right answer, it's fine. So there we go for the properties of angles of polygons. Finding the measurements of, finding the sum of the interior angles is found by taking a polygon and dividing it into triangular regions and multiplying that by 180. The interior angles of a regular polygon are basically that number, that sum divided by this number of sides or the number of angles that there are. And the exterior angles always, for any polygon, have a sum of 360 degrees. Okay, so those are kind of basic polygon related angle things that we're going to be looking at. The remainder of this unit, pardon me, is really going to be spent focusing on certain types of quadrilaterals and their properties. But as always, guys, thanks for watching. If you have any questions, be sure to email them to me or leave them to me in the comment section of the Google Classroom. I'll be happy to help you. Until next time, thanks for watching and take care.